somebody just please confirm that, because I'm using another microphone and I want to make sure that
yes,
I'm well.
We can hear you fine, thank you.
Okay, thank you very much. So first of all, welcome, and it's a great pleasure to have you all here, and we very much appreciate. We know how difficult it may be. To all of you who are here in person, and to all of you who are here remotely, thank you for joining us. I would like to say that this is a great pleasure and privilege to being able to open the center, to lead the center, and I hope that there will be some nice science coming out of this. And in this talk, I want to roughly give you an idea what we are doing, why we are doing this, and why this is important. And in order to get the right perspective, I think we need to go back roughly 2,500 years to understand how mathematics was developed throughout the time. And well, if we go very, very much back in the history, then people were starting to ask very fundamental questions about the world. Well, is it flat? What is the shape of the place we are living in? And probably the first person who realized that what is the real answer was Pythagoras. He was doing this by observing quite a rare astronomical event, namely the lunar eclipse. And what Pythagoras realized was that, well, what we see in the eclipse is nothing more than the shadow of the Earth that is actually, well...
Excuse me, Pavel, are we supposed to see the slides? I mean, I don't see them.
Thank you very much. I knew that I forgot something, and the thing I forgot was to share the screen.
Yeah, this would be great.
And you should also pin the video.
I think so. Right.
I mean, the participants should also switch to.
Yeah, let me just make sure that we are in the right place. So we don't need this one.
Now I see the slide.
So the question is, do you see Pythagoras right now?
Yes.
Good. So we are in a good shape. Thank you very much.
I don't see you. I don't see you.
I think you are not missing the best part.
Okay.
Okay. Sorry again for this misunderstanding. So, Pythagoras started to think about various geometrical solids. This is where geometry was born. It was born to answer very fundamental questions about our world. Roughly 200 years later, Eratosthenes from Cyrene put a little bit of quantitative measure on that. By doing certain simple astronomical observation, not only he was able to see that this is really a ball, but he was able to measure the circumference. He was the first to realize that if you sail west far enough, you will be able to get to India from Greece. And we really needed to wait quite a long time for a practical application of this idea. And that kind of starts a new field of what we may call analytical geometry. And throughout many centuries, mathematics was developed as an applied science, was developed as a tool to abstract away certain ideas and to give an answer to questions which are of the fundamental importance. Let me give you another example. If we look at the Principia Mathematica by Sir Isaac Newton, obviously we know that this is the basis of the Newtonian theory of gravity, but it's also a basis for the modern calculus in mathematics. And they all came hand to hand. So the idea was we are trying to answer questions about the universe, and we are developing rigorous mathematical tools to do that. Later on, what happened was, the amount of knowledge was increasing and increasing, and in the 18th, 19th, and especially in the 20th century, we got an increased specialization of fields. So mathematics itself became a huge organism with its own hypotheses, which are coming from, abstract considerations. And oftentimes it happens that the abstract ideas of mathematics are coming back into practice, giving new development. Let me just mention one of the huge development, which is modern cryptography, based on the symmetric or asymmetric crypto systems. Anytime you are buying something online, even the connection, the security of the connection we have right now is secured by abstract theorems in number theory, which were not developed for the purpose of building a crypto system. They were developed inside pure mathematics, and then they were imported to applied science because they were the right tool to use. Okay? So, coming back to mathematics and application, what we are planning to do in the Dioscuri Center for Topological Data Analysis is to do application of mathematics. And there are essentially two ways to do it. Well, first of all, you need to talk to people outside mathematics, to the people in applied sciences, to the people in medical sciences, economical sciences, etc., etc. Then you need to understand the problem. But once you understand the problem, well, quite often there is already a theory in mathematics which can be adapted and used. Sometimes we need to develop new theory, a little bit of new theory, just to make this figure. I think what makes us in applied mathematics different from the pure mathematics, I really don't believe that there is a huge distinction between them. But the one I was able to find is that, well, what is our motivation? For the Dioscuri Center in Topological Data Analysis, the motivation to solve the problems is because they are important to somebody outside mathematics. They're not solved. There is a need of rigorous mathematics, and this is something we can provide. But the important thing to realize is that applications and pure mathematics are something like yin and yang. They really need to go together, and they cannot be separated. Advances in pure mathematics imply advances in application. Applications give a challenging question to pure mathematicians to think about. And this is what we are doing. There's one more aspect which cannot be neglected, and this is something also Professor Zauerman mentioned, which is the implementation. Quite often, well, you can have a perfect theory, but you really need to have algorithms and efficient implementations to make it practically useful. This is something we are doing as well in the Dioscuri Center, or in topological data analysis. So, let's actually take a look at the name of the center. So if you don't happen to be a mathematician, well, this bit about data science, it's quite clear. But this topological bit may be a little fuzzy. And let me give you an intuition why this is all about, what this is all about, and why this is important. Shortly speaking, topology allows to describe shapes up to continuous deformation. We think about it as a non-rigid version of geometry. Okay. So, shapes. Why are we interested in shapes? Why they are important? And in order to explain this, let me go back again to the ancient Greeks. So there's a paint illustrating the allegory of a cave. The allegory of a cave is a fundamental concept in the philosophy of Plato. And the idea is that, well, we are here. We are the prisoners sitting in the cave. And what we see are only shadows of real objects. We don't see the real objects. And by the way, those real objects over here, those actors in these scenes, they are the ideal objects. So what I'm trying to say is that oftentimes we see different versions of objects. None of them is ideal, but we kind of understand that they are all impersonification of some ideal quantities. To give you an idea, well, what we can learn from a shape. It turns out that we can learn quite a lot. If you are into dogs, you probably will be able to recognize the species, the races of dogs, just by looking at the shape of them. Okay, so this is why I believe understanding shapes is important, and we will have many, many more examples for that quite soon. Let me talk to you quickly about topology. So again, it's a science. It allows to understand shapes up to continuous deformation. And what do I mean by that? Well, essentially, I can deform a shape in any way. There are two rules that I cannot break. I cannot tear, and I cannot glue. Everything else is acceptable. And the animation we see over here is kind of an extreme example of two objects that are equivalent to continuous deformation. So we have a coffee mug. If we deform it continuously, it's equivalent to this torus object, or if you wish, a tire. And also from the perspective of topology, those two objects are not distinguishable. And when saying this, you may ask yourself, okay, hang on, that's pretty general class of deformations. Why can this be of practical importance? Well, what I'll try to do right now is to motivate to you this is really the right language to speak about shapes. That's the right language to understand the shapes, because we really understand shapes, meaning the platonic ideas, up to continuous deformations. Okay, so we started with dogs. Let's move to my second favorite animals, horses. So if you Google horse, pictures of horse, you'll probably get the images like this. And what we see over there is different pictures from different angles in different motion phase. They are all continuous deformations of idea of a horse. Moreover, if we look at the movie presenting a horse, so this is one of the first motion picture movies in the history of humanity. The differences between the constitutive frames, well, the following frame is just a continuous deformation of the previous frame. And as humans, we can recognize that this is really a motion. If we put them together and run them in a reasonably quick way, we'll see a motion picture. Every frame is just a continuous deformation of the previous one. Well, we can put the idea of continuous deformation much farther, still being able to recognize that we are dealing with an ideal object of a horse. And our brain somehow is still able to recognize that. And that's why topology is a very useful language, because it kind of is doing what our brains are doing implicitly. Understanding shapes up to continuous deformation. So let me just tell you that you really don't need to go to see Picasso's exhibition to convince yourself about it. If you are using public transportations, for instance, in Warsaw, and you want to buy a ticket, you'll probably find a map of certain buses and the tram lines in Warsaw, with the places where you can buy tickets from this automatic ticket machine. And well, even if you don't live in Warsaw, you realize that the streets are very straight. The distances between stops are very uniform. This map is not accurate geographically, because the road bends. The distances between two stops, they are not uniform at all. But for the purpose of understanding and for the clarity of understanding, it is much better to continuously deform the reality and get a map like this. And you can still gain good information out of this. So this is something, in principle, we are using every day without actually realizing that we are looking at the topological deformation of the reality. Okay, so this is kind of a motivation why topology may be important. Let me speak a little bit more about what we are doing in the center. And there are essentially two ways we are using topology. One of them is to use it as an abstract descriptor, as a gadget that allows to summarize important information in the data. So we have data which is complicated. We don't know how to compare different complicated objects. Well, if we compute their topological invariance, then this comparison became easier. And we'll see examples of that very, very soon. Another example is, when we are building topological models of data, of processes. And let me quickly, very briefly, and I'll try to do it as intuitively as I can, give you an idea what are the mathematical tools we are using over there. And then we'll move to understand why we are using this. So the credo of my community, credo of topological data analysis, is that data has shape has meaning, and meaning brings value. And it's kind of a common knowledge if you think about it. So suppose we take a sufficiently large cohort of people, and for every person, we take two measurements. We see how much the person weighs and how tall the person is. And over here, and we put those data in the scatter plot, and where the x-coordinate is the height, and the y-coordinate is the weight. And if you look at this data from far enough, you'll realize that they happen to have a linear shape. Moreover, using least square methods, we are able to find an algebraic equation that describes this line along which most of the points are concentrated. And if you ever check your BMI, your body mass index, it's precisely a consequence of that algebraic model, because for the certain height there is a certain optimal weight for you to have. I believe I'm somewhere above the weight, but that's another story. And you may realize that there are some persons which are quite far away. We consider them outliers in a sense, so they do not fit the model. Therefore, they don't have a good BMI. Perhaps, they may want to do something about it, but most of the population is on this line. And the reason why, we can have the BMI, we have this model, is because this data happen to be linear. However, if you look at the natural phenomena, most of them don't happen to be linear, and we see a huge amount of different possibilities. For instance, data may be cyclic. And that happens very often if you are encountering some periodic phenomena. It can happen also, for instance, when you're looking at the activity of a genome of a person who is at the healthy state, it becomes sick, and it's moving to some other state. But then when the person became sick, the immunology system kicks in and brings the person back, hopefully, to the healthy state. But it's bringing it back throughout a different trajectory. It's not backtracking. So what we see, if we see an evolution from healthy to sick and back, is also this type of circular data set. Our data set may be of the shape of a figure 8, and that's something we encounter quite often looking at certain chaotic phenomena. Letter Y or X, we call it a Y junction, X junction. There are different interpretations you can put on that. For instance, the center you may consider as a normal state, and all the branches as different types of diseases, right? So some sort of abnormal states. And the point is, we started from algebraic model that describes the relation between weight and height. In principle, we can try to build algebraic models to fit in each of those scenarios. The problem is oftentimes you don't know which of them we are encountering at a given moment, especially because those point clouds, I draw them in the plane, but typically they are living in very, very high dimensional space. And therefore, you may, in principle, do an algebraic models, but what we are doing in TDA is something different. We are trying to put a combinatorial model in place that is not taking any assumption about the type of equation we want to fit in. Instead, let me just give you a quick idea what do we make it to do. So we start from this Y junction over here, and what we do is we select a subset of points which are kind of uniformly spread among our points. And then we put balls of a radius r around those colored points over here. Well, if we pick the radius large enough, then every black point will be covered by at least one of the balls we obtained over there. And then we are building something which we call the one-dimensional nerve of that cover. What does it mean? Well, it's essentially a graph. The vertices of those graphs corresponds to centers of the balls. And the edges put between two vertices, even only if the balls happen to have non-empty intersection. So by doing this, we are ending in this graph, this combinatorial representation, which is telling me that my data is having a kind of a heavy center plus free outliers. You may think about them as free abnormal states. Right, so that's one of the examples of topological models we may build. I also mentioned that we can use topology to build descriptors of data. And the working horse over there is called persistent homology. So idea is, again, we start from a collection of points in some high dimensional space, and we put a ball of the radius r at every of those points. And then we let r grow from 0 to infinity. And we are looking at the sum of those balls and look at the homological features of them. So we may be looking at the number of connected components, number of non-trivial cycles, number of voids. And we gather this information in this algebraic gadget we have here on the right-hand side, which is called a persistence diagram. It's quite a complicated algebraic gadget, but the bottom line is it allows us to compare objects which are difficult to compare otherwise. We'll have an example very, very soon. Okay? So I was speaking quite a lot about trying to infer some information from the point clouds. Of course, there is a well-established branch of mathematics, namely statistics, which is already doing this. And statistics is an extremely powerful tool. However, well, there are numerous examples. For instance, this Datasaurus data set, which shows that, well, we may have different collection of points which have very different shape, as you can see, which have essentially the same statistics. And my take on that is that, well, statistics is an extremely powerful tool, but we should use it alongside with some methods that are telling us something about the shape. And that's precisely what we are doing in topology. So we are using statistics alongside with those methods of building models, computing persistent homology, which I just described. Okay, so I give you a quick intuition on how. Let me tell you what you can do with this. And there's one more remark. I should have made it at the beginning. So if you happen to have any questions, I more than welcome this. Both for our guests over here and also for the guests remotely. Please feel free to unmute yourself, and I would be very happy to go deeper into certain topic if there is an interest in that. So we got that very, very brief intuition of how we are doing things. Let me discuss what. And I will start from material science. I will start from chemical engineering because, well, it's one of my favorite applications of topology. Even Johannes Kepler used to say, well, when there is matter, there is a geometry. Kepler was speaking about geometry because topology wasn't existing at his time. But I'm pretty sure that if he was living nowadays, he would be speaking, well, when there is a matter, there is topology. And over here, we are looking at the descriptors of some so-called nanoporous materials, like zeolites or metal organic frameworks. And we want to understand the structure of the pores of those materials. How we do that? Well, we sample a collection of points from the pores, and we put the balls over there, the radius r, and we let the r grow. By doing so, we are getting those persistence diagrams that describes materials. Okay, why this is important? Why this is useful? It's because there are databases of so-called hypothetical nanoporous materials, which contains easily up to millions of different materials. And those are very useful objects. They can be used, for instance, to capture CO2. They can be used to store methane. They can be used as catalyzers in many chemical reactions. And then there's an obvious question. So we have those vast database of hypothetical material. And I want to find the best material to capture CO2. Which one is it? Well, obviously if you have millions of potential materials, you cannot go to the lab and synthesize every single one of them and try to find experimentally. So obviously you need to use some numerical methods. And there is a way to predict the performing property of a material, which is essentially based on quantum Monte Carlo simulation. However, this is also quite computationally costly. And trying to do 1 million quantum Monte Carlo simulation, well, it's still not really feasible computationally. It is prohibited. And but what we realize is that certain materials, for instance, zeolites, they have similar shapes. They have similar properties. So if I know that certain shape of pore is good, I better look around for similar shapes. If I know that certain shape of pore is bad, I shouldn't waste my time and computational effort to check for the similar ones. And by using this topological information, we can cut a lot of unnecessary computations and just concentrate on the best potential materials and carry on quantum Monte Carlo further on. And this is really because those gadgets, those persistence diagrams, they allow us to compare materials. They allow us to say, well, what's the distance between two different materials? But, there's much more we can do with this. Thinking about regression in the space of persistence diagrams, we hope, well, to find a path of materials in this very abstract space of different crystallographic structure of better and better materials, and we want to follow this path to being able to find even better hypothetical materials. Taking solubility, so if the material really, if you can mix it with water, chemical stability and more, it's also potentially can be done by looking at this topological summaries of the materials. And everything can be done quickly. Everything can be done in silico in our computers. That's one of the applications in the material science. If you're not into material science, let me speak about biology. Let me speak about medicine. Each of us have a very nice nanoporous structure in our body, namely the spongy bone. So we have it in our backbone, we have it in our wrist, we have it in our hips. And unfortunately, in a certain occasion, there is a disease. The bone is suffering, and for instance, one of the diseases is in osteoporosis. And in that case, well, the bone became weaker, and it's much easier to get certain fractions. That's a scenario which we would like to avoid. So if you look at the diagnosis, medical diagnosis right now, the gold standard to detect osteoporosis is to look at the density. So we take a unit volume and we see how much bone it is over there. If there is a lot of bone, you're fine. If there is not enough, well, better to start certain treatment. However, when talking to medical doctors, talking to specialists in osteoporosis, they can give many examples of patients who have very low bone density and still don't suffer any osteoporotic fraction, and of the patients who have high bone density, but they suffer osteoporotic fractions. And obviously there's a hypothesis, well, there has to be something more than density. Because if you have a structure which is organized in the right way, it can have very, very low density, still being extremely robust. So our proposition, what we are doing right now, is to trying to apply topological methods to understand the structure over here and structure over there, and see if we can tell them apart. So this is a joint work with Richard Abel from Imperial College of London, and well, he had this kind of unique data. Those are micro CT scans of the vertebrae, so which is a part of your backbone. This is just one slice, one vertical slice. It's taken from two different patients, the same gender, roughly the same age. One of them suffered from osteoporosis, the other did not. And what we can see is, yes, the density is different, but there's much more to the story over here. So, the structure over here is much coarser than the structure over here. The vertebrae over here are much larger than the vertebrae over there. The number of cycles, this is something that is supporting the weight. It's much larger for the healthy patient and for the osteoporotic one. So then we started to apply the tools of computational topology. And the question was, well, by looking at the structure, not the density, the structure of the bone, can we predict how robust it is? And this is a very preliminary result, but yes, it seems we can. We got a correlation up to 70% with the structure, taking away the density. And this number seems to be much better compared to density. The last sentence, please take it with the caveat that we still need to check it properly, because unfortunately we don't have a densitometry data on those bonds. We only kind of trying to estimate the things. But what is the main message over here? Well, hopefully, looking at the structure and topology is the right language to do this. We may be able to provide a new diagnosis tools in osteoporosis, which may be able to tell apart those patients with low bone density, but a good structure, they are on the low risk of having those bad fractions, from those with high density. So that those patients with low density but good structures, there will be false positives for osteoporosis. We get positive results, but they don't have osteoporosis. Those with the high density who get fractions, there will be true negatives. If we do densitometry right now, they will say, okay, you're fine. But you leave the places in which examination was taken, and you may get a fraction. That's a true negative. And we hope to be able to capture them by looking at the topology of the structure of the bone. Let me stay for one more example in the material science. So this is a joint work with Victor Zavala group from Madison, Wisconsin. And what we are looking at is this LC, liquid crystal signatures of different compounds. Liquid crystals, I mean, you all have this in your microwaves or in old-fashioned calculators. And they're essentially, a collection of crystals that are, if they're iso-oriented, you just can see through them. If they don't become iso-oriented, then you don't see, and in one case you see white, in the other case you see black. And I believe when they become not iso-oriented, you start to see black region. And what is happening is, well, we have certain contaminant that is penetrating this array of liquid crystals. And the liquid crystals are reacting in a certain way with this contaminant, and we are getting those pictures, the movie of which we saw over there. So what the Victor Zavala group did, well, they used a deep convolutional neural network to try to tell apart different contaminants. They were quite successful in this. However, they're also quite well aware that by using deep convolutional neural networks for a small sample of images, they're overfitting a lot. They are prone to those adversarial examples. And what we started to do is to use topology. So we are looking at how the topology of this structure is changing as the contaminant is penetrating the liquid crystal. And we realized that we also get very good accuracy. This time we are having something very stable with respect to any errors, any models, something which is not sensitive to those adversarial examples. And why this is important? Well, it allows to tell apart different collections of contaminants. And over here I just have two examples. One of them is water, nothing harmful, but this DMMP, that's a very serious thing because it's a main component of biological weapons, like for instance the sarin gas. And this technique may potentially gives a sensor, a real-time sensor, that are able to detect certain threats, which works in very, very stable way. Okay, I love material science, but let me step back. Let me speak about other nice geometrical structures which are very close to our minds, namely the neurons. So those are just two-dimensional projections of digital reconstruction of different types of neurons. We have 80 billion of them in our brains, and that's a joint work with neuroscientists and mathematicians from Dubai. And what we are looking at, different ways of comparing neurons. You may ask why. Well, there are numerous hypotheses in neuroscience. For instance, if the pyramidal neuron from one region of my brain is, by any means, statistically different from pyramidal neuron in another region of my brain, if we take a group of patients with certain neurological disease and the control group, can we spot any differences in the shape of neurons? In other words, is the disease really originating from the neurons or maybe from the connections between them? And in order to be able to answer this, and numerous stable descriptors that potentially may allow to answer this question. Okay. But mathematics is mostly about abstraction. So we are abstracting away unnecessary details. If I wouldn't tell you that those are neurons, it wouldn't really matter to you. What we are looking at are trees or graphs embedded to three-dimensional space. And they're extremely common otherwise. You may think about polymers, you may think about biological tree structures, or you may think about, if you are especially into medical applications, vascular trees or the lungs. And this is a plot actually taken from a paper done by the group of Professor Jacek Brodsky from the University of Southampton. They're collaborating quite extensively with this group. Well, they're using topological tools to understand the shape of our airways, of our lungs. They're able to show that certain diseases like COPD, they do have an effect of the shape of our airways. Right now, together we are trying to get the data obviously from the control group, but also from the group of people who recover from COVID, to see if there are any changes in the architecture of our lungs that may be caused by the virus on the long term, after people actually recover. Because during the infection, obviously there is. We know. The question is the long term. We are trying to get the data for that study. Speaking about COVID, I mean, it's a very hot topic. And if you are doing data science, obviously you want to try to understand better what's going on. You may be dreaming of trying to help with that thing. And, well, we are trying to do this as well. Back in March, I said, well, I'm doing data science. I want to try to do something. And I was looking for some genetic-based data sets, some blood test data sets that describe patients with COVID. And surprisingly, they almost do not exist. Nobody gives away data at that time. The only data set I was able to find is coming from one of the hospitals in São Paulo, Brazil. And this is essentially an image from a 15-dimensional data set. What's the data set? Well, when they are admitting people to a hospital, they're making a blood test. They are looking at 15 parameters of the blood test. So I believe that if you go and ask for the standard blood test, you will also have 15 different parameters. Well, the question I was trying to pose, and let me make a very, very strong statement right now. Whatever I'm going to say is not clinically validated because this data set is way, way too small. So we are still looking for larger data sets. We are still not able to find it. But the hypothesis is, well, maybe patients with COVID, they happen to have certain combination of these 15 parameters of coming from the blood test. Maybe if you have certain combination of those parameters, you are more likely to have COVID. And in this data set, we indeed see that, if you are in this region of this parameter space, and we are looking at certain model of 15-dimensional entity, then you have 20-25% of having COVID. If you are over here, you have something like 30% of having COVID. So there seems to be a signature related to this. And then we ask a follow-up question. Well, those tests were done on the admission of the hospital. Where are the people who eventually end up in the emergency care unit, in the ICU? And they also seems to be even more located. Again, we are looking at extremely small samples, so this is not validated in any way clinically. It's not validated because we don't have an access to that data. But potentially we are kind of dreaming of doing this. And once I realized back in March that there's no data for COVID, we actually teamed up with our collaborators from Oxford University to start to build a database. So we haven't done anything to Topological, but we try to do the service to the community, trying to gather the information about epidemiology, various sociological context, economical context, try to understand how non-pharmaceutical intervention may or may not be successful, and which of them may or may not be successful. So we built this big database, hoping that people in epidemiology, social, political sciences may find it useful. Okay, speaking about social and political sciences, and I promise you this is one of the last examples, but it also, I think, shows the mission of the studies, the research which is not done by us. This research is done by Simon Rutkin in collaboration with Monmouth Council. This is one of the councils in Wales. It's over there. I think Cardiff is over here and Bristol is somewhere there. So it's just in the English-Welsh border. And Simon is he's an economist. He is using the tools, software tools, which we are developing in order to understand socio-economical variables. So what the Monmouth Council and Simon is doing, well, they are giving a set of questionnaires to the people living in this area. There are multiple questions over there about your income, about how many cars you have, do you own a house, do you happen to have successful professional life, etc., etc. One of the questions which is particularly interested to Simon is, well, are you happy? Can you actually, what is your level of happiness from 0 to 4? So what Simon wants to understand is how the other factors affect the happiness. So he took, I think this is quite high-dimensional data set, but he wants to understand what is the distribution of happiness, which is essentially a discrete variable, across this data set. So, well, he get this plot, and he was actually looking at this big connected component, which is consisting of people who are, the level of their happiness is as high as it can get. But if you look at this, you realize that there is an outlier. So those people are with essentially all the characteristics very, very similar to the people who, well, describe themselves as being very happy. But those people are kind of in the middle range. Okay, so I'd like to say that there is a button in our software which say, well, explain what makes those people different from those people. We don't have a button because we don't have a graphic user interface yet. So you need to really type a command, explain. So when Simon actually did type the command, he realized that essentially all the variables are the same, except those people over here, they're not technically skills with modern technology, like modern smartphones, computers, internet. It's not that they cannot afford it, but they cannot use it. And the Simon as an economist is trying to suggest certain policy changes so that those people can be bring up in their self-reported level of happiness. And that's an example of how the tools, the software we are producing based on topological ideas can be used not only in material science, biology, medicine, but also in the social and political sciences. And the notion of shape is very fundamental. It's almost as fundamental as the notion of number. So it means that I could go for a long time and want to go for a long time. But there's one more point I would like to make, and I think it's kind of my obligation as applied mathematicians to make. Namely, well, there's a question why it pays off to invest in mathematics in general. And there are two ways you can answer this question. One of them is, well, in Poland we have this fantastic tradition of having very good mathematical graduates in computer science. Especially those in computer science, they have strong mathematical backgrounds. That's very different in Poland than in other countries. And we also have very good mathematicians, very good computer scientists. That's extremely beneficial from economy. And there is no question about that. What I would like to talk about is why it really pays off to invest in mathematical sciences, in research. And there are many examples. Let me give you just one of them. So what we are looking at over here is an illustration which is kind of an evidence for the Moore's law. So the Moore's law, well, he's still alive. He's very, very senior right now. Back in the 60s, he was a CEO of Intel. So they were doing chips, computer processors. His observation is essentially that the number of transistors you can put into a single chip double every 18 months. So swapping some details under the rug, you may say, well, the computational power double every 18 months. So computational power per month. So I have a fixed budget right now. I can buy a computer. But if I wait 18 months, I will be able to buy a computer which is twice as much, twice as powerful as the one I would buy right now. So if you double something by moving every fixed amount of time, this is a manifestation of an exponential growth. This is what we see on the y-axis over here. So this is the number of transistors. This is the time. This is exactly the same exponential growth that is driving, unfortunately, COVID cases and deaths right now. That's a very, very bad news. But I want to speak about something optimistic, which is the Moore's law, which is the exponential growth in our computing capabilities. But when you think about important thing to realize, this is driven by billions of euros, billions of dollars. Intel, AMD, and NVIDIA, they're all putting huge investment to continue this curve further on. What I want to say is that, well, when you are doing the computations on your computer, what is really happening is we are solving certain mathematical problems. And the point I want to make is that there are many examples of the collections of problems in which we also make exponential progress in our ability to compute. One of them are the LP solvers. So this is linear programming solvers. There are certain optimization methods. So you want to optimize certain gain investing as little as possible. Well, if this gain happens to be a linear function of our input variables, then it can be solved by the IP solvers. And if you look at the history of how it was developed, starting just after the Second World War, we had an exponential algorithm. It was totally unfeasible. But then there were 5, 6, or 7 landmarks in which this complexity was brought down. Eventually, right now, we are looking at the cutting-edge algorithms, which are quadratic with respect to the size. So using mathematics, by understanding the problem well, we can also gain similar or even better speed up than with the computer hardware. Let me give you one example from my research. So I'm also working with electrical engineers, and they're interested in solving Maxwell's equations using certain formulation. Well, in that formulation which we are looking at, they need certain topological information to make this formulation run. And this topological information are representatives of generators of first cohomology group of a certain complex. Well, and I actually start to work with my collaborators, Ruben Stocconi from Italy, on that problem when I was still a PhD student in 2007, 2008. Well, we set up a theory quite quickly. We understood what is the mathematical object we want to get. And then what we did was to took off-the-shelf software and try to do the computations. Well, we did the computations. Something came out from very small mesh. But if we look at something which can be considered an industrial size mesh, we're not able to finish the computations because they were simply too hard. Then we realized, okay, we have a working theory. Everything is fine, but you cannot make an impact for the engineers because we cannot solve the problems which are too large. And then we start to look at different ways of, well, making the computations feasible. We introduced certain heuristics, which brought us from, no, we cannot compute it, to, yes, we can compute it. We need 60,000 seconds, but in principle, we can compute it. Just to give you a reference, once you have this topological information, you essentially need half a minute to finish the computation. To get the information in 60, so it would be, let's say, 60,000 seconds. So it was in principle possible. Again, it was much too difficult. But then we started to develop theory much further. We realized that there are certain aspects which are not interested to us. We can do it in a bit different way, still achieving what we want to achieve. And then we brought it down, the computational time of this cohomological basis to 25 seconds and subsequently 1 second, which became a small fraction of the whole problem. And that's kind of an example of the development which can be given to you by mathematics, which you cannot achieve by just waiting for the right processors to come. And I think this is also very important to realize that the computational progress we are having nowadays is partially, there's a very, very good portion of it due to the hardware, but also software is becoming faster. And it is becoming faster because the mathematics behind it is pushing it to be faster. So we often also have an exponential progress in algorithms. Again, this progress in algorithms is kind of much cheaper than the progress in the hardware. Okay, so this was about the general need of applied mathematics. Let me speak about the center. So we have multiple research connections to many of our partners, mostly in Europe, in the United States, a little bit in Asia, in Australia. We are not working actively with them at every time, but they are using our software, they are using our ideas. They are very much interested in working with the center. And the moment we are growing the center right now, and we will be using those connections to make this really international center, centered in the Institute of Mathematics, for example. What I was trying, the point I was trying to make is that when you really want to take mathematical tools, bring it over the fence to applications, you need a strong support. We have a fantastic support from the Dioscuri program. We also have a fantastic support from our colleagues in the mathematics department. And already I got a numerous conversation with them. They are all very eager to help, very eager to collaborate. We have our partner from Bremen, Dmitry Kozlov, from the Institute of Algebra, Geometry, Topology, and Application, also helping us to settle this down. And we have those multiple, but it's very wide network of collaboration. So our target is, well, very inspired by real problems. We have rigorous mathematics and efficient solutions that we can offer to solve them. And well, if you want to reach us online, you can do it on our webpage, on the Twitter, on Facebook. But I would be really looking forward to talk to you about the ideas, the problems you may have. And ask you, is there something we can do, the type of shape of analysis we are doing in the cell. So having said that, thank you very much for coming. It's a great pleasure to be here. Thank you.